Hello, and welcome to today's webinar, Circularity Solutions for Cotton, Turning Textile Waste into Environmental Benefits, sponsored by Cotton Incorporated and brought to you by Cotton Works. I'm Jesse Daystar. I'm the Chief Sustainability Officer here at Cotton Incorporated, and we're excited to connect with you today. At Cotton Incorporated, we provide a wide range of information, technical assistance, and innovation to support companies with their cotton business. This includes apparel and home textile to fiber products in health and beauty space. As a not-for-profit organization grounded in science and research, our mission is to help companies succeed in their cotton-related business. Through cottonworks.com, we offer a comprehensive resource for cotton sustainability information, resources, and assistance, all for free. Whether you're looking for detailed technical information on cotton or seeking expert guidance, Cotton Works has got you covered. We encourage everyone to register as a user and take full advantage of these resources. Feel free to submit your questions and comments at any time through the overall presentation. We will get to those questions and answers towards the end and address any of those questions you have. Additionally, a replay of this webinar will be sent to you via email and be available on cottonworks.com. All right, now we got the intro out of the way. Let's jump to the presentation. So I'm going to kind of give a overall big picture on circularity and our research at Cotton Incorporated, and then we're going to pass it off to our guest, which I'll introduce just a bit later. So kicking this all off, kind of a big picture framing of the apparel industry. We recently did a study published in Nature Communications that identified the apparel industry as contributing 8.3 million metric tons of plastic leakage to the environment. That's sort of like pollution, essentially unmanaged waste that gets into the environment. So think the bottle on the side of the road or a polyester t-shirt thrown on the ground or the synthetic microfibers coming off our laundering into the oceans, into the water. That's plastic leakage. And that's about 14% of the entire global plastic leakage. So the apparel industry is quite significant in the plastic issues around the world. 8.3 million metric tons is a hard number for my brain to wrap around. So we came up with kind of some weight equivalents. So 820 times the Eiffel Tower or 9 times the Golden Gate Bridge. So quite a lot of plastic from the apparel industry ends up in the environment, unfortunately. You may have heard of this to take, make, waste linear system. This is a picture of plastic leakage I took on the Outer Banks of North Carolina. I like to go out there and spend some time at the beach, of course. And yeah, you can see it everywhere. And a lot of times it's there and you can't see it. As we think about circularity, there's what you call a butterfly diagram from the Ellen MacArthur Foundation, quite popular in the realm of sustainability. It's split into two different sort of paradigms here. You have the renewable material on the left-hand side, which cotton would be part of. And then you also have the side on the other side, the non-renewable, more finite materials on the right side. So synthetics and oil-based products would be on that area. So we're going to dive into how we can leverage cotton's circularity within these more renewable systems within this presentation. But thinking a little bit more about the supply chain, what happens to our clothing when we're done with it? It's very complex. And to take it from more traditional landfill or traditional end-of-life situations and to wrap that back into something like a textile-to-textile recycling loop can be done, but it is complicated. This is some great work by Accelerating Circularity, where they modeled the different and represented the different steps that would need to be there in order to have a overall textile recycling industry. And it is complex. And I think the industry is filling in areas within this overall mapping of the supply chain. However, we're not there yet at the scales to really solve the plastic waste, to solve the textile waste issues that we have today, particularly with up and coming regulations. So we need to look at things beyond just textile to textile recycling. Also, circularity in itself isn't inherently sustainability. They're related, but they're not synonymous. So a recent study came out a bit ago. It said that growing cotton doesn't produce a lot of emissions. So recycling cotton may actually have a higher environmental climate impact than simply harvesting more cotton. And another study found that renting clothing may not have really any benefits. So Whenever we come up with circularity solutions, we have to run the numbers, have to do a life cycle assessment and look at, is this in fact better than what we would have done otherwise? Because otherwise we're investing time, resources, and steering the industry towards something that's not going to achieve our outcome of improving environmental impacts. So we bring a lot of that rigor in environmental assessment and life cycle assessment to our circularity research at Cotton Incorporated and throughout the industry. When we think about our efforts, we like to focus on a few key areas. First, as I really harped on there, environmental benefits. We want to make sure this is actually helping. Also, we need to find solutions that can be economically viable. Of course, there's a technology ramp up and you got to start somewhere, but something that does actually have a future in economic viability that could occur at a scale that matters. And that's the next key focus area is, can we get this to scale? Is this some pipe dream that doesn't have the technical rigor or the technical capacity to really get to a large scale? Or, kind of really looking at that. Finally, we look at gaps in industry efforts. We don't want to be redundant of the private industry. We're not for profit, focused on research. So we want to fill the gap that is uniquely cotton related and help solve for solutions that really help natural fibers and cotton. So we really don't want to be redundant and leverage our effort in finite resources. So focusing a bit more on cotton and also just in general renewable resources, we have a very circular system in a lot of ways, and that's the carbon cycle. Plants through photosynthesis, whether it be a tree or a cotton plant, pull CO2 out of the atmosphere and create the stalk, the seed, the roots that go into the ground, maybe even put some carbon into the ground, but also put carbon into the cotton that we're wearing. The CO2 that is in hopefully your cotton t-shirt your cotton t-shirt was CO2 floating around in the atmosphere. Warming the atmosphere now is actually on you, warming you. So it's pretty neat that we can, as a plant and material, cotton can pull CO2 out of the air, but eventually it will biodegrade, assuming we don't do something else with it. So if it goes to a landfill, it goes to compost, or ends up in the environment, cotton has been shown to biodegrade in all these different scenarios, releasing the CO2 back to the atmosphere. So sort of nets to be zero. However, what if we did something else with that? What if we kept that CO2 locked up for long periods of time? What benefits could we achieve that way? So when you look at the actual cotton plant, this is a Sankey diagram from one of our recent LCA efforts. On the left-hand side represents all the different carbon molecules or tons of carbon that are actually coming in to the US cotton production. And then a lot of that goes to above ground residue, think the cotton stalks. A lot of it goes to the cotton seed. Some goes to the gin byproducts. Some goes to the soil. And most of that typically goes back to the atmosphere of those sources I just listed. It'll eventually cycle back through that carbon cycle. Some gets permanently sometimes stored in the soil as soil carbon increases through time through practices that are like regenerative agriculture or improved soil health. But some of it is temporary stored in your clothing, as I referenced earlier. So there's definitely opportunities in any of these carbon flows to lock that up long term, capturing carbon, potentially offsetting the emissions of producing the cotton. Today, we're going to be, I think, a bit more focused on the temporary carbon storage in the lint and the cotton itself, but we'll probably touch on a bit of these throughout the presentation. So we can capture carbon from these byproducts, from these waste materials, maybe in a very cost-effective way. Meanwhile, billions are being spent to create carbon capture technologies, pulling CO2 out of the air. So CO2 molecules floating around, coming out of your mouth and into the air, around 400 parts per million. That's going up through time, but it's very dilute. Meanwhile, cotton is very concentrated in terms of the carbon and CO2 that was once in the air. So leveraging plants to get us a good part of the way there to fully captured as compared to spending billions to pull CO2 out of the air. It's a different way of doing it, but I kind of showed this slide just to say there's a lot of resources and money trying to figure this problem out. And it is a real problem that I think cotton has a chance at really helping with. Another interesting revelation and happening just recently on January 16th of this year, Google actually made the largest biochar purchase to capture carbon out of the air. So 100,000 tons of biochar carbon removal by the company by 2030. So this is a way in which taking plant materials and creating biochar sort of like charcoal from plant materials, can capture carbon long term and benefit these companies looking for carbon insets or carbon offsets to reduce their scope 3 emissions and overall climate impacts. So here's just sort of a few more pictures. You can have various different units. This is one by Biochar now. You might see a little bit more later, but there's different ways you can heat the material, the biomass, or the plant material up in absence of oxygen, sometimes with a vacuum. Various ways to achieve this, but the ultimate on the right-hand side here, biochar can look something like that. So now I'm going to pass, now I've kind of warmed everybody up, I'm going to pass the control over to Dr. Joe Segas, who is a excellent professor at North Carolina State University, helping us research circularity and ways to capture carbon. He focuses on really figuring out financially and environmentally friendly ways to pull carbon out of the air and store that long term. So with that, Joe, Dr. Segas, I will pass it over to you. Thank you.
Okay, thank you, Dr. Daystar, and hello, everyone. As Jesse said, I'm a professor at North Carolina State University in biological and agricultural engineering, and I'm excited to talk about this opportunity to convert cotton waste to biochar, right? I think there's a lot of value creation potential and also a lot of carbon removal potential. There we go. All right, so Jesse did a great job introducing this concept of carbon sequestration, carbon dioxide removal. So it's referred to in various ways. I typically just call it carbon removal. And I want to double click on that for a moment because I feel like it's really important to understand why we are so invested as when I say we, I'm talking about the sustainability community, the climate community, industrial producers who care about decarbonization. Like, why is carbon removal on the map? And so I like to use this metaphor where you can think of our atmosphere as a bathtub. And right now, there's about 3 trillion tons of CO2 equivalent, which means predominantly CO2, but other greenhouse gases floating around in the atmosphere. And to Jesse's point, very dilute. Every year, we put in about 55 billion tons, right? So you can kind of think of that as the water coming out of the faucet. To hit our decarbonization goals and to achieve net zero and limit global warming to a point that's not devastating, we at some point should close this valve entirely, right? But most experts have now realized that's not really practical, certainly not in the near term. And so carbon removal is another path. It's the drain in this metaphorical bathtub, right? It allows you to take some of that emissions out of the system. And so you don't have to close the valve entirely. We should, and we should strive to close it and reduce emissions, but carbon removal allows us another path. And so most experts believe by mid-century, somewhere between 5 and 10 billion tons will need to be removed per year. And so I like to pose this question to audiences like you all, which is carbon removal considered linear or circular? If from a physical sense, it is quite linear because we're just taking molecules of CO2, getting them out of the atmosphere, preventing that warming, and keeping them stable in some solid liquid form on the ground or underneath the ground. But if you look at it through the circular lens, right, it's really kind of a net zero outcome where the carbon is recycled over and over. And so there's a bit of a debate right now. I like to think there's actually good synergy between carbon removal and circularity. And I'm going to touch on that a little bit in this presentation, but I published some papers on that comparison if you're ever interested in learning more. I do want to go to the market though, because this is a great slide, I think, to illustrate how this particular market, the carbon removal market, is growing rapidly. And most of the demand is coming from large tech companies like Microsoft, Google, Alphabet, Meta, as you can see on the left. And a main reason for why they are buying carbon removal credits is to mitigate their emissions from all of the energy they're consuming for AI. Artificial intelligence, as everyone knows, is exploding, and these companies are building data centers and power plants to power the data centers like crazy. And they need to offset or remove those emissions, and that's where carbon removal comes in. And so if you look at these two plots, starting with the plot on the right, on the top on the right, It's showing the total tonnage of CO2 that's been purchased, CO2 removals that have been purchased up through 2025. You can see it's a nice growth curve. Um, Interestingly, in the year 2024, 86% of all carbon removal credits sold were from biochar, right? And I'm going to get to biochar more in just a moment. And that correlates to about $10 billion worth of carbon removal credits sold to date, right? So it's a pretty large market. The bioeconomy, and Jesse alluded to this, the bioeconomy is a great opportunity for low cost near-term carbon removal because unlike direct air capture, which are giant machines trying to pull CO2 out of the air, um, photosynthesis has done a lot of the heavy lifting for us. And so we have all of these different streams of biomass, including cotton, right? And cotton textiles already in the bioeconomy with very concentrated CO2. And so this plot here, or this figure here, is trying to show the various sinks of carbon in green and emissions of carbon in orange throughout the bioeconomy. And the idea here is to achieve a bioeconomy where the sum of the quantities of carbon in the green arrows is greater than the sum in the orange arrows, and that would enable what we call a carbon negative bioeconomy. And so there's a few different ways you can keep the carbon from returning back to the atmosphere through degradation. You can capture gaseous biogenic CO2 at ethanol refineries, at biopower plants, etc., and you can inject that deep underground. There's some infrastructure challenges there, but it certainly has a lot of potential. Another one, which of course is noteworthy today, is biochar. And we're going to get to that in just a moment. And the other one I want to point out is taking bioproducts like textile waste and simply landfilling it in a way that prevents decomposition. And that's being referred to as biomass burial. Now, I do want to pose another question to the group. This is a bit more of a scientific one, but it's one that in my community, a lot of people are grappling with, which is what's the best use of biomass waste, including cotton waste? Is it for energy production or carbon removal? Some might say both. But this study, I've included the citation to down here. I recommend checking it out if you're interested. They asked this question, they took a quantitative approach, and they made this plot. And I don't have time to go into exactly how this plot works. But what it's showing you is that at a certain price of carbon on the x-axis, right, biomass waste becomes more valuable for carbon removal than it does for energy. And so, for example, if you're trying to replace coal with biomass, but Microsoft says it's going to pay you, some dollars per ton CO2 for carbon removal instead of energy, what this plot is showing you is that as long as Microsoft is paying more than $25 per ton of CO2, which they are, it makes more sense to use biomass for removal than energy. Okay, so a bit of a long-winded intro into carbon removal. Let's talk about biochar. And by the way, just a quick little preface, biochar can certainly be used for more applications than just carbon removal. I'm going to get to those in a bit. There's a lot of agronomic benefits that are exciting. So what is biochar? Biochar is a carbon-rich, highly porous, and solid material produced from a process called pyrolysis. And it treats biomass under high temperature, 400 to 700 degrees Celsius, in the absence of oxygen. So very importantly, this is not incineration and it's not combustion. If you look at the bottom right, this gives you a very high level sense of what's going on. The biomass comes in, it's treated at high temperature, and there's three products: biochar, syngas, and pyrolysis oil. If you track the carbon, right, about 30 to 50% of the carbon ends up in the biochar. And in the top right, like Jesse showed before, it looks a lot like charcoal, right? It's a very carbon-rich material. And it's inert. It's not reactive, which is why it's a great means to sequester carbon, since that carbon will not react and go back to the atmosphere, as long as it's treated properly. I'll get to that more in just a moment. Okay, the cotton industry in the US has a lot of potential here, right? So if we look at the three primary waste types, the cotton textile waste, predominantly post-consumer, cotton gin trash, and cotton field residue in this table shown on the left, you can see that the total amount of dry tons is around 16 million dry tons available per year. About 10 million of that is from the cotton textile waste. If you make some pretty optimistic assumptions on how much of that biocarbon can be stabilized, there's the potential to remove around 30 million tons of CO2 per year from these three feedstocks. And if you sell every removal credit at $150, that would net out to be around $4.4 billion per year in revenue just from removals. Just to give you the scale of this potential market opportunity. I just want to double click again on textile waste because that's the one that represents the largest opportunity within the three feedstocks I just showed, right? At 10 million tons, 3 billion in revenue potentially just from these materials. In my community, which is carbon removal, bioprocessing, not many people are talking about textile waste, right? And that's why I'm really excited to hear Scott talking a bit because Scott is the pioneer, at least in the US, to my knowledge, who's taking these textile waste materials and doing something with it on a commercial scale. But we need more people to talk about this opportunity. Lastly, just to touch on briefly, pyrolysis has been shown to degrade a lot of these hazardous polymers like PFAS that are sometimes present in various textiles. So it's good to treat them with different techniques like pyrolysis. Now, I already showed those three different feedstocks, which are the dominant ones. This is showing you a bit of a process flow, starting with the carbon in the atmosphere to give you a bit more of an idea of exactly where these streams would be collected, right? So of course, the most important part is well, to me, the most important part is you're stripping the carbon out of the air through photosynthesis, right? You're making the cotton material that's going into textiles, right? And there's really just three different opportunities. You can take waste at the field level, like Jesse had already mentioned, stocks being the dominant form of waste at the field level. Then you have pre-consumer waste, which some might consider cotton gin trash as one of those pre-consumer waste, but there's others. And notably, there are not good data on the availability of the pre-consumer waste. So we don't really know super well how much of this material is available. Then you have post-consumer waste, right? And these can be collected, thermochemically converted through pyrolysis to biochar. And then once you make the biochar, what do you do with it? The most common application is in the soil. And I'm going to talk more about that in the next slide. But importantly, other things can be done with the biochar. And there's a lot of innovation happening in things like putting it in concrete, right? There's some advantages of putting biochar and it helps to sequester carbon. Using it as adsorbent materials for pollution control, catalysts as a coking material in steel production, and also in electrodes. Lots of different opportunities with biochar. But again, the biggest opportunity in terms of a current market growth and scale is putting it in the soil. And so this is a plot, field plot that's managed by my colleague Alex Woodley at NC State, where he's been loading biochar in these small field plots to look at the agronomic impacts. And so biochar has been shown, of course, it can sequester carbon, and I have this permanence range from 100 to 1,000 years, and that's a big range, and there's a reason for that. So stay tuned. I keep leading you all on, but stay tuned. I'm going to talk more about that in a second. Some of the agronomic impacts are important though, right? When you add biochar to the soil, you can reduce runoff, which will reduce eutrophication and over-fertilization of waterways. You can decrease the soil organic carbon loss, reduce the nitrous oxide N2O emissions, very potent greenhouse gas, and importantly, increase crop yields. So some physiochemical properties that are very important when looking at biochar are things like the yield, the surface area, the morphology, and the carbon, hydrogen, nitrogen, and oxygen contents. Now, I just led you on, so here's where I was going. When it comes to how stable is the carbon in biochar when it's applied to the surface of soil, there's a lot of uncertainty. And so my colleagues and I published a paper in 2023, taking the best data we could find and fitting what we call sort of like a durability or a stability curve here, which is showing how much of the carbon is retained in the biochar on the y-axis over time. And this is a log scale starting with 10 years, 100 years, 1,000 years, and 10,000 years. And what you can see is that up to about 100 years, most of the carbon is locked away. But after 100 years, there's a lot of uncertainty. Error bars go through the roof, and we just don't know when it's applied to the surface. That's why there's some companies who are burying the biochar because it gives much better stability and therefore much lower risk of carbon reversal, which is important when you're selling carbon removal credits. All right, coming to the final part of my presentation, I want to quickly give you all a glimpse of a study I completed funded by Cotton Incorporated, where we took let me see, three different textile waste materials: 100% cotton, a 50-50 blend cotton polyester, and 100% polyester. And we pyrolyze them at three different temperatures: 400, 500, and 600 degrees Celsius. And we wanted to understand what the differences in morphological properties were and what the different applications could be. So starting here, moving left to right, I'm showing some microscopy images of the same magnification. So each one of these shots is at 500 micron scale. And you can see on the far left, we have the 100% cotton textile, right? This is the biochar material, our product that we're imaging, very zoomed in. And what's interesting is that the cotton fibers, the cellulose fibers within cotton, which are woven together to make the textile, their morphology is retained, which is pretty interesting, right? You can make out the fibers very clearly. For the 50-50 blend, you can see that there's been some sort of disorientation of the fibers, and they've actually been agglomerated together, right? And I'm going to go into more images in the next slide to try to explain what's going on here. And then for the 100% polyester, it's a glassy type, very brittle carbon, which was what we expected, but nonetheless, we wanted to confirm it. Okay, so now we're looking at more imaging, cotton on the top, the 50-50 blend in the middle, and then the polyester on the bottom. So again, looking at the cotton, moving left to right, we're increasing magnification, zooming in on one of those cotton fibers. And you can see that the morphology really is retained. In the 50-50 blend with polyester, especially looking at that second from the left image, you can make out the fiber morphology, but it's been melded together, right? And that what's happening here is during pyrolysis, the synthetic polyester is melting because it's a polymer. It's melting before the reaction with the cotton fibers takes place. And so that's kind of fusing all the fibers together. And then at a certain point, the fibers begin to pyrolyze, which is basically some of the mass is volatilized out and it's making biochar, right? So it's sort of an interesting morphology. Whereas with the polyester, it completely melts and then it turns into a brittle carbon material. Now, I'm getting to why this really matters in just a moment, right? So first, let's look at the biochar yield. I mentioned yield is really important. Well, not really unfortunately, but just how it goes. Biochar yields from cotton materials are quite low because it's a lot of cellulose. And so you can see on the plot on the left for the three different temperatures, all of the yields are somewhere between 15 and 20%. So what that means is if you have 100 tons of textile waste, you can make about 15 to 20 tons of biochar, okay? Now moving to the plot on the right, this is what was really intriguing. The cotton polyester blend shows a much elevated surface area. All right, and surface area is basically how porous the biochar material is. All right, it's a very important feature when you put it to soil because it helps with water retention, nutrient retention, fertilization, and the cotton synthetic blend had way higher surface area, and we believe our hypothesis is that during the pyrolysis process, um, when the polyester melds the fibers together, once the fibers then begin to pyrolyze, they release gas. And that gas has to escape through the melded molten polyester, and that creates a bunch of tiny pore spaces, which gives you really elevated surface area. So pretty interesting finding. We haven't published a paper on that, but it should be coming soon. And so I'm coming to the end here. I want to just go through these so everything is really driven home. Biochar is a stable form of biogenic carbon that can remove carbon from the atmosphere and provide ecosystem services. The demand for carbon removal via biochar is increasing rapidly, as I showed earlier. Nearly 85% of removals in 2024 came from biochar. About 30 million tons of CO2 could be removed, right? This is a ceiling, but it gives you an idea of the scale through cotton waste in the US, giving around $4.5 billion in annual revenue. Uncertainty exists in the durability and permanence of biochar when applied to the surface. That's why there is quite a bit of interest in actually burying the biochar now for removal. But you can certainly still use biochar for agronomic benefits like crop yield and runoff, etc. The polyester cotton blend had remarkably high surface area, right, which could actually benefit the soil. And so, Cotton Incorporated is funding my group to continue exploring the opportunities for biochar from cotton textile waste. We're looking at techno-economic feasibility for centralized and modular production. And we're doing a geospatial optimization that will actually generate plots like the one shown here in the bottom right, where we'll optimally site various pyrolysis operations of different scales, showing the transport of the textile waste and the biochar to give an idea of the actual potential on a granular level in the US. And so with that, thank you for your time, and I'll pass it back to Jesse.
Thank you so much, Joe. Dr. Sagas, that was a great overview of some of the science, some of our research, and looking at this from a very scientific perspective and identifying the big picture, but also literally the small picture and what that biochar actually looks like on the surface. So now we have, actually, before I get to this, just a reminder, please enter any questions you have for Joe or Scott or myself throughout this presentation. So next, I'm going to give control over to Scott Coleman, who is a co-founder of Recircled and has a long track record and history of working in the apparel industry and innovation surrounding sustainability. All right, Scott, I think you might have control. So we'll pass it over to you. Feel free to give more introduction should you need it.
Great, appreciate it, and thanks Jesse, and thanks Joe. What my part of the presentation is how can we and how are we pushing this along to commercialize it, size and scale, and how can we create revenue from it, so we don't have to have subsidies around it, and so hopefully that's what I can demonstrate to you today. And Jesse, I think you might have to move the screen for me. So there you go. Thank you. So here's a picture just to highlight what we're working on. So on the left-hand side of the screen, you can see nice, neat piles of textiles and colors. As most or a lot on this call may know, that mechanically recycling textiles, particularly cotton, has been going on for decades. But typically, this is where it's taken from. It's very clean. It's very pure. It's not a lot of contaminants. But the big problem is what you see on the right. Just massive, massive piles of very contaminated textiles that we don't know what the blends are, what's on them, what they're coated with. And that's what we're solving for. Okay, next slide, Jeff. So here's just a classic how and I know Jesse touched on this a little bit on how and what happens to textiles today, where you can see on the bottom, there's some reuse and resale going on. Industrial rags are being made out of it. Shoddy and stuffing is being done. There is a big movement around textile to textile recycling with lots of challenges with that. And then landfill. And what we're doing is now adding on a couple of other opportunities around what we can do with all of these textiles. Okay. So I found this interesting, and it really relates back to the textile to textile recycling. This is not around cotton, it's around polyester, but it just demonstrates some of the challenges we have around textile to textile recycling. And it's not that we're trying to downplay it at all. We think it's fantastic, but we're just addressing the challenges. You can see here, this was a study done in the EU where you can see that within polyester, there's over a 1,500 euro gap between recycled polyester and virgin polyester. And so those are the challenges that we're facing, and hopefully we can help add additional systems on, as you'll see in a minute, that not only will close that gap, but completely reverse the gap. Okay. So what we're calling this is material transformation. We believe that circularity can happen at the molecular level, and we're doing it in two ways. The first way we're doing it is what we've been talking about on this webinar, which is pyrolysis, or something called thermal cracking. As it was explained to me, because I'm not the PhD on this call, is that it's speeding up nature is really what we're doing. Is we're taking it back to the carbon level, and you're going to see some of the testing results we have from it and the percentages of carbon we're getting out of textiles, which is amazing. And pyrolysis is the classic way to create biochar. We've recently been introduced and are developing something called hydrothermal liquefaction, where one of the byproducts is also biochar. We believe that there's room for both. The good news with pyrolysis, we get incredible results. The great thing with hydrolysis, we can use wet, any blends, anything that we want, and including it handles all things like PFAS and just nasty chemicals and so forth. Okay. So this is, and I know we've talked about thermal cracking. We thought this was a pretty cool slide that we put together. Just kind of gives you a where it goes, how it happens. So Jesse on his slide had that amazing graphic from the Accelerating Circularity, where it's very complex around accepting textiles, sorting them, where they go, what happens to it. And you can see with a pyrolysis process or pyrolysis type process, it simplifies it. It's really not that hard to do. And you just get amazing benefits from it. So not only doing textiles, before we did textiles, we actually used leather waste is what we started with incredible results. And we're now doing tons and tons of leather waste every single week with the great results. Okay. So this is a process, and so this is Biochar now in Berkeley, Colorado. Not all pyrolysis is created equal. This is a very unique system in the fact that, as Joe said, you're using temperature and pressure. Biochar now is unique in that they use time. These are kilns where the biomass is in the kiln for 10 hours. And it creates a biochar that's completely amazing. But what's really cool about this process, as you can see, is the many, many kilns here. And I believe that Biochar now has 72 kilns on site. But the great news is if one kiln goes down, you're not shut down for the day or two or three or four. You're still operating. You're still going. The other great thing about this is if you look at the simplicity of it, the simplicity of these kilns is quite simple, and they can literally be built anywhere on the planet. So I know we're talking about North America and the US right now, but as you know, textile waste is a global issue. And so we love processes that are simple, easy to understand, not capital intensive, and things we can build anywhere. So hopefully you can get a snapshot of that. Okay. So these are, and I know they're very, very small, but these are testing results. On the left is the testing result for 100% polyester, and on the right is 100% cotton. The biochar community, when you look at, I think it's a one, two, three, the organic carbon, which is the third thing down. With polyester, we created 92% carbon, and with cotton, it's almost 94% carbon. Which is very, very, very high on the carbon scale. So we were super excited when we saw those very, very, very high percentages. And if you want to see these testing results or other testing results, we're happy to show them to you at any time. Okay. So this is so people ask, what is hydrothermal liquefaction or HTL? So we put together a little animated video which will play now, and it'll kind of tell you what it's all about.
think the sound is actually not coming through, Scott, unfortunately.
Okay, well, let's move on. This is on our
We-
YouTube channel, and
we'll do that.
we'll push it on. Yeah, let's go to the next slide. Um, Yep, there we go. So if you want to look at the size of a hydrothermal liquefaction unit, this is a size that can take about 3 tons of product per day, and run it through it. And one of the things you didn't see on the slide, there's basically 6 products that come off hydrothermal liquefaction based upon the feedstock. They're biofuels, natural gas, liquid mineral fertilizer, biochar, and a gray water, with incredible efficiencies of up and over 90%. Again, we like this process. Both pyrolysis and hydrothermal liquefaction are not new. They're decades old. It's just how they've been applied. And like pyrolysis that you could see with the systems, although the capital level needed to build these systems is more than pyrolysis, we can still build them very efficiently and in small sizes and put them anywhere on the planet. So we see between these two processes, HDL and pyrolysis, we have an opportunity to clean up basically the fashion waste that's around the world and turn it into great things. The other thing that we're doing with HDL with those 5 products is we are adding on a generator system to the end as well, so that things like the biofuels and the natural gas can get turned into electricity immediately and go right back in the grid, or supply electricity to the factories where we're taking care of the waste and so forth. So just a little snapshot and more on HDL to come, but just create some great processes. Okay. So why pyrolysis and HTL? And this is really just to wrap it up. Is that it's scalable. It's something that we can do today. We can build either system very small, where we're handling, as 1 or 2 tons of waste a day, or they can be built very, very, very large to handle thousands of tons a day. We believe that flexibility is very important, particularly around transportation, so that we can build these systems where the waste is at, so we don't have to be transporting it, miles or even halfway across the country to take care of it. And the units can be built on site. And so that's where we're working with wherever the waste is at. It could be at landfills, it could be at a factory level, it could be at a DC, it could be on agricultural property where you saw where there's a lot of waste from cotton growing. They can be used for that. So lots and lots of different purposes and built where the waste is. Um, and to the next slide, we want to reduce transportation. It's crazy with what's going on. And so with that, I'll turn it back to Jesse, and we can start to. Oh, there we go. Quick ROI on these things that we can demonstrate to you. It's a 2 to 3 year ROI, which in the financial world is a crazy number. Operational costs are very, very, very low. With HTL and pyrolysis, we now can handle all waste. And we're at the moment we have a working on optimization of the output. And the beautiful thing about it is to operate these, we need absolutely no subsidies to do it. We can create enough revenue from the byproducts with both of them to operate it. So back to you, Jesse.
Excellent. Thank you so much, Scott. It's really neat to hear how a commercial entity is taking the science and trying to solve real world, real industry solution problems with these solutions. And really excited about your interest in cotton and overall sustainability. So with that, we're gonna kick it over to some Q&A. And I apologize for the sound not working on the video earlier. We will send that out along with the link to that along with the webinar. So jumping into some questions, for those who haven't entered anything yet, please do. Maybe we could start with Joe and then maybe just Scott to speak about, there's somebody says this is very exciting. What might be the environmental impacts of pyrolysis? So maybe speak a little bit to carbon emissions as well as maybe something around the lines of other types of emissions. So I'll start with Joe, then pass it to Scott.
Yeah, thanks, Jesse. That's a great question, and I should have explained that during my talk. I apologize. One of the great benefits of pyrolysis for biochar production, if your primary product is biochar, you can run pyrolysis with no external energy needed, right? And the way that's possible is because during pyrolysis, you're putting off a gas, right? And that gas can be has condensable and non-condensable components. Doesn't really matter. The gas has a lot of energy in it, and so you can combust and burn that energy on site to provide the heat and power needed for your whole biochar production facility. And so that's one of the, like I said, great benefits when it comes to the carbon emissions, right? They're very low in terms of what the pyrolysis does itself. And that's important because if you're trying to remove carbon from the atmosphere, you have to prove through life cycle assessment that you are net negative, right? Overall, over the full life cycle, you're actually removing carbon. And that's only done if you have very little external fossil emissions. So that's an answer with regards to the emissions life cycle.
Scott, you care to add anything there, or you think that covered it?
Yeah, I mean the beauty of it is because as Joe said, we know that, and when we look at processes for handling all this, we want to be able to place systems anywhere in the world. And so, if there was a problem with emissions, if there was a problem with that wouldn't work someplace, then it becomes less interesting. The good news is this works everywhere. Pyrolysis going on globally, has for decades. It's nothing new. It's just that based upon what we have, it's a great opportunity to use it and expand it for other means.
Great. And another question that kind of builds on that, tagging Joe on this one, the cotton polyester blend, how does having a polyester in there affect emissions and or the carbon aspects?
Right. Well, since the polyester is derived from petroleum, right, you're not going to have any carbon removal benefit from that polyester carbon, right? So it doesn't help you, if you have 1 gram of biochar from polyester cotton, right, it's not all 1 gram of that is going to contribute to carbon removal because a fair percentage of it is from polyester. So that's one angle with regards to the emissions impact of polyester on biochar. There are some other potential, I'd say, unknowns right now when it comes to the char. You can't really call it biochar, but the char that's produced from polyester, how it behaves in comparison with cotton-derived biochar, right? There's lots of data on converting cotton and other cellulose-rich materials to biochar. Like Scott said, it's a safe material to put in the ground. But polyester char, there needs to be more trials done, right? And I think there is a lot of active R&D in this space with great sponsors like Cotton Incorporated who are actually looking at what happens if you take a synthetic blend, make biochar, and put that in the soil.
Interesting. Interesting. Thank you, Joe. Another kind of question tagging related to that, and maybe Scott or you can start with this one. The chemistries applied to textiles. What are your thoughts on what happens to those in those very extreme conditions of a pyrolysis or those other units you mentioned? What happens to those? Is it an issue? Is it contaminate the product? Or can you explain a little bit about that?
Yeah, again, Joe can probably explain chemistry more than I can. But what we're finding is you could see in those results, you're doing this at a very different level, and so that's where a lot of those chemicals. So think of all the things that we put on textiles, from water repellency, fire retardancy, all those types of things dissipate in some way, and either are turned into things that aren't so bad from the results we can see, and literally neutralizes. As a matter of fact, we're running a test not on the HTL system, which will produce biochar with PFAS right now. It'll be done in September, and so we'll show that the PFAS completely dissipates from it. So that's a good thing. So a lot of the worries we've had around some of the nasty chemicals we use within textile production, it looks like we can handle all of that with these two processes.
Great. I think that's an excellent answer. Another question came in about the durability of biochar. And I'll kind of start this one off a little bit and pass it to Joe. Within the textile and the cotton industry, there's a variety of ways to create carbon insets or carbon offsets. Carbon insets being different in that, say, a cotton farmer was to create capture carbon and sell that carbon benefit to the downstream supplier or purchaser of the cotton. So it keeps that carbon benefit within the supply chain or value chain. So one way in which we're actually creating carbon insets is through doing regenerative agriculture practices such as reduced tillage, cover crops, and nutrient management, where you actually store more carbon in the soil. It's generally thought to be pretty long term, but maybe there is some reversals and there's some uncertainty there. When it comes to biochar, it is certainly, I think, more durable and can keep carbon locked up sometimes better than those practices I just mentioned. But there is some uncertainty around it. So maybe Joe, you could speak a little bit to time frames and the general standard for looking at permanence, like the 100-year rule.
Yeah, for sure. And I'm more familiar with the voluntary carbon removal markets. And so, there's a couple standards that the carbon removal registries are using now, right? And one that comes to mind is made by Isometric, right? And they have two different types of carbon removal credits that can be sold and traded for biochar. The 100-year credit and the 1,000-year credit, right? And the way they differentiate between the two is primarily the percentage of carbon that's in the form of what they call inertinite, which is basically a structure very similar to coal. Okay, and so if you can produce biochar with a lot of inertinite, which looks very similar to coal, then it is, at least it should be, much more stable. The uncertainty comes in to play with the lack of data that we have on actually putting these biochar materials, even if they are seemingly very durable through the analytical means that we use to measure them. There's not enough actual field level data, right? And coal is buried underground, so it's different than coal put on the surface of soil where it interacts with water, light, microbes. And so I think 100-year, there's really good confidence there. So that's promising. Like that means no matter what, biochar has a major role to play because 100 years of high durability carbon removal is very valuable. But some companies prefer 1,000-year. They want permanent removal. And so for the 1,000-year, there's more field trial data required.
Excellent. Yeah, so pretty good durability, but more research to be done there. All right, great. Got a few more minutes for questions, and maybe this is a one kind of maybe start with Scott and then maybe Joe. It's talking about like how would you actually implement some of these things? There's a question about maybe could you implement one of these at a textile mill for the waste that's there, and then somebody else who I believe is a cotton farmer indicated that could you put this at a cotton gin and use the gin byproducts to do this? Is that something that's a reasonable scale at those levels, or does it need to be much larger? How would you think about that?
No, that's exactly how we're thinking about it. And it's really we ask the question, where is the waste at first? And then the second question is how much waste? And then what is the makeup of the waste? What is the feedstock going to be? And based upon answering those questions, we can scale systems to that. And that's why we like both pyrolysis and HTL, because we can make them very small or we can make them incredibly large. We are showing that obviously larger systems are more efficient, and so forth, but the idea of having them in a cotton farm and using all the agricultural waste and pyrolysis is up to this point has mainly used timber and agricultural waste and biomass like that. So it's absolutely perfect for that. But you can think of factories where factories, I've spent my lifetime in factories, and the amount of waste that's produced at these factories is just tremendous. So imagine a day where all of them have a pyrolysis and an HTL system where at the end of every day it's going in and it's creating the byproducts that then they can actually reuse. It may be biofuel that gets turned into electricity and then it's powering the factory. That's entirely possible today, and that's what we're proving out. So, or it could be landfills. We see municipalities. So imagine at a small town where we can put this at the landfill, and rather than going into the ground, it's going through and turning into biochar. So just the opportunity is almost endless, is the way that we're looking at it.
Thank you so much. Joe, have you looked at the aspects of scale in terms of there's different ways to do this, obviously. So maybe speak at some of the research you've done there.
Yeah, definitely. I haven't looked as closely at HTL, but I have spent some time looking at HTL. But with pyrolysis, you can what we call downscale with relatively good economies of scale. And so when you're building any type of biomass conversion plant, um, the economies of scale are really important. And so traditionally, the bigger the plant, the cheaper the overall production cost, right? Because you get the economies of scale. And as you make a plant smaller, the unit cost, so the ton of biochar produced, becomes more expensive. Biochar is pretty simple, right? And that allows it to downscale nicely. HTL is more complex, but it's also, relative to other types of refining, pretty simple. And so they do downscale relatively well. And biochar, I can speak more, or sorry, pyrolysis, I can speak more to because it's so simple that it can be done on a small scale.
Great. And I think we have time for one more question. What kind of testing, Scott, would you do for your product to look for contamination or the quality? Can you just speak a little bit to your rigorous testing before that product goes out the door to whatever life it lives?
Yeah, so like everything, certifications and testings and things like that are, it's all volunteering. So we're building out what does that look like. And so if we're throwing in, particularly mixed waste that we have no idea what the contaminants are and so forth, are we literally going to test every single kiln that we pull out? Hopefully we'll build a system without that. I can tell you there's nothing really good in place at the moment. And we aren't at the moment. I can tell you we are trialing with many, many tons waste that we know where it's from. We know what it is, and we can specifically test that. But I can assure you that with the engineering that we have going on at the moment, that within the next 12 months, we'll have an incredible process to make sure that the byproducts coming out meet standards of whether they're set by somebody or that we'll have to set ourselves. So more to come.
Awesome. Well, again, I thank both of you for contributing your time and expertise today on the call and sharing all this great knowledge. I encourage everybody to check out Dr. Joe Segas over at NC State and Scott Coleman at Recircled. Thanks to both of you, and thanks to everybody on the call for a great engaging conversation with the Q&A and your attention today. So with that, we will conclude the webinar, and I encourage you to keep an eye out for the recording and to visit Cottonworks. Thank you very much. Have a good day.